So here's a video that I'm actually recording live, so I have the other students here. I want to do three things in this video. Something we've actually already seen here but I didn't record. I'll go over again quickly so that those who are not here in Castle can see it. Then I want to look at something, the X-empty example, which I think was mentioned in an earlier video, and then give a quick example of how we can use CoCoALib to do some computations. So let's have a quick look what's happening here. So I've actually opened one of the files that's inside CoCoALib, and this is a definition of one of the functions. So the function's called prev prime. We see it in red here. So this is C++, by the way. This is C++. Perhaps I should just remind you quickly of the syntax here. So this is a function definition. So firstly we specify the type of value it's going to return. That's called small prime. That's something that I've defined, or is defined in CoCoALib. We'll see what the definition is shortly. So the type of the value it's going to calculate, the name of the function, and then between round brackets the types of the arguments, the types of the parameters. In this case it's just one parameter, and it's a constant reference to a machine integer. Here we can really think of that as just being a long. So it's just one parameter here, and then the function body is between these curly brackets. So we have a begin curly bracket and an end curly bracket. We have another one inside, that's for a loop. I'm not going to go through the entire function, I just want to go through some aspects of it. So first thing we do here is a sanity check on the value that was handed in. So C++ will automatically call this function only if we supply a machine integer as a value. If we supply any other type, either the compiler will say, sorry, can't do that, or it'll call a different function with prev prime. So we want to do a sanity check on the machine integer that was handed in. So if it's negative, or if it's in fact too big, that's a little bit unclear what this means, we're going to report an error. And we do that in CoCoALib by calling, strictly speaking, it's a macro, cocoa_throw_error. It's actually better if we just put in two strings here. So the first string should really be not non-negative, and then the second one is really telling us which function encountered the problem. So it's prev prime of some integer n, and here it actually repeats the message saying n must be non-negative. So this is not well written here, but the main point is we should call cocoa_throw_error. The first thing should really be what the error was, and the second one is where it was discovered. So it was discovered in prev prime n. This one's perhaps a bit better. Turns out if the number's so big that it won't fit into a signed long, then we throw an error saying arg too big. So the value was too big, and the function that found it was prev prime.n. So this is how we report errors inside CoCoALib. And we go on, we actually get the value into n using this function here. Now the bit I actually, there's one more, another error case to check here. Not only do we reject negative values, we actually reject any value that's less than 3. We know it's an integer, so that leaves only 3 values left, 0, 1 and 2. So if n is 0, 1 or 2, again we get an error. Here apparently it's out of range, and the error is that there's no previous prime. So finally, after these few lines here, we've now actually got down to, we know the input's sensible and we can actually calculate something. And it's just these first 3 lines that I want to look at. So these are the easy cases. So if n is equal to 3, then the previous prime is of course 2. But 2 is a machine integer, and we have to tell it that we actually want a value of type small prime. So we're going to call a constructor here. And this is a constructor that takes 2 arguments. So it takes the value 2 and a second argument called arg_is_prime. And this is simply telling the computer that we're guaranteeing we already know that this value is prime. We've already checked it, or we know for some other reason that this value is prime. We do the same here. If n is let's see, 4 or 5, then the previous prime is going to be 3. Again, we guarantee it's prime. And if it's that seems a bit strange. If it's less than 8, oh yes, of course, it's 6 or 7, then the previous prime is 5. Otherwise, we go into a loop here. We don't want to go into the details here, but we'll notice that the loop is actually calling the prime test here, is prime n. So we keep going around the loop until is prime certifies that the value really is prime, in which case we return the answer. So once again, even here, even though we don't have a constant value here, we know that the computer has already checked that it's prime, so it's done the check, so we can put in this extra guarantee that the value it's returning is prime. So this is a definition. This is part of the file numtheoryprime.c. So files that end with .c are the implementation files. They contain the definitions of the functions. This one's about 1,000 lines long. Now we go to the .h, which is the header file. This contains definitions of new types, new classes, and declarations of functions. We'll see what they are shortly. So I've gone to the .h. This is a header file, and this is now the definition of the new type, the new class, small prime. So something we've created. We're creating it here. So the keyword class says that we're defining a new type here, a new class. Its name is small prime, and again between these curly brackets. So curly brackets are used a lot in C and C++ to enclose blocks. So this is the beginning of a block, this is the ending of a block. And then inside we have two parts. We have a public part. These will be mostly functions that anyone is allowed to call, and then a private part, in this case where we put the data member. Now here the data member is actually very simple. It's just a machine integer of type long, so that's a 64-bit integer typically, and nothing else. So we've already seen that a class may contain 0 or more data members. 0 is unusual but permitted. This one contains exactly 1. The computer can be very clever, the compiler can be very clever, and any value of this type here is in fact occupies just as much space in the computer as a machine integer, and we can calculate with it just as quickly. So the bit I wanted to attend to here is we have two constructors for a small prime. So small prime is our own type. We're defining it here, and we have to tell the compiler how such values can be created. And there are two ways of doing it. One is we can just hand in a machine integer, a long. If we do that, then the computer, this is relatively slow because the computer will explicitly call a check for primality. If the value is not prime, it will then give an error, saying, sorry, I can't create a valid object of type small prime because the argument you gave me is not a prime. And the other one that we've already seen being called here is this, it's a second constructor which has two arguments. The first one is again going to be the value that we want the prime to have, and the second one is this, it's called small prime flag here. In fact, we can also see what the definition is here. This is you'll need to learn a bit of syntax to C++, but after the colon, we're initializing the data member myval. We're initializing it with the value p, and then the extra instructions we do, we just call a CoCoAssert. So CoCoAssert will not normally be executed. It's only executed if we turn on the debugging mode for CoCoA. So we should already, if you're calling this constructor here with a small prime flag, that means you're guaranteeing that p is a positive prime, and so strictly speaking we shouldn't need to check anything here. Of course, if your program goes wrong, there's a bug somewhere, and it could be that by some mistake you actually did try creating a small prime with a negative value. So when we turn debugging on, this would then check to make sure that the value is not negative. I suppose, come to think about it, that should actually be greater than or equal to 2. So I just modified the code here. The computer will know about it next time I compile. And there's small prime flag, so we could simply have put in a boolean here, perhaps a boolean called p is already prime, or some name like that. But I think in this case it's better to have the small prime flag. This is something we've actually defined up here. It's an enum. There's only one value of this type, so an enum has just a finite number of possible values. There's only one value of this type, and its name is argis prime. The computer internally will represent it as some integer, I think. They're actually not entirely clear about that, but so this is the only way we have of creating a value of this type. And then the second line simply this is essentially privately declared, and then argis prime here. This line here makes it available for everyone to use. So if we type argis prime, it's actually interpreted as small prime flag : argis prime. The : simply says we have a class here, the name of the class, and then a member inside. So the : here is essentially the class name and the name of the member. So this is its full name, a bit like you would have someone's family name and someone's first name. So I just wanted to show you quickly the definition of a simple class here. So this one's really quite simple, and a compiler can be clever, and while it looks like there's a lot of extra baggage being carried around with a small prime, the compiler itself carries this baggage, and it knows the extra properties of small prime. But the code that it produces, the computer will actually run after compilation, will be highly efficient. It'll essentially just be keeping this long value, a machine integer, and it'll operate directly with that. So I think that's all I wanted to say here about this num theory prime. Oh, no, there's one more thing I did want to say. So this is the header file. So in the header file, we have the definitions of new types. So class is the keyword we use to define a new type, and its name was small prime. We have some more. I don't want to go through those at the moment. And then further down, somewhere near the bottom, I'll just scroll down. Not like that, I won't. Oops, got my microphone in the way. So I wanted to do Control V, I pressed the wrong key. So this is the part I wanted to look at here. So the other thing that we have in header files is a bit like a menu or an index or a contents of functions that we are going to define somewhere else. So the functions are defined in the .c file, which is the implementation file, and the .h file is the header file. For the compiler, the information that the compiler sees here is enough to do the compilation. So we have a function called isPrime that takes a machine integer and returns a boolean. We have another one called isPrime that takes a const reference to a big integer and returns a boolean. We have 4 versions of isProb prime. We have next prime, prev prime, random small prime. These ones here, for example, guarantee that they return values of type small prime, with the type we've just seen above. So the information we have here is enough for the compiler to do its work. So if in my program I want to call next prime, then the compiler will check to make sure that the value I've given it is a machine int to work with, and it knows that whatever next prime produces, it's going to be a small prime. And it has enough information to deal with that. So the compiler doesn't need to see the definitions of the functions all the time. These are just declarations. This is the information necessary for compilation. Splitting your code into header files and implementation files is normally necessary if you want to contribute to a library. If you just want to write your own program, you don't normally need to split it into 2 parts, or at least not initially. You can just put it all together. So I think that's all I want to say about this. What I'd like to do next is look at this example xempty. So the examples are all in the CoCoA. So you've downloaded the CoCoA sources, and you will see that there's a directory called examples there. And the examples all have names ex minus something, and the rest is supposed to be helpful. The one we'll look at today is ex minus empty.c. So .c is the suffix we always use if we have C++ implementation code. Now xempty.c is quite a long program that does essentially nothing. So all our examples look a bit like this. So they start off with an include CoCoALib-L5 So library.h is in fact all of the header files for the CoCoA library gathered together in one big file. It's also convenient to put in this magic phrase here. I'm hoping you'll get to learn a bit more C++ and you'll find out what this does. Basically, this says that any function from the standard template library, and they that belong, if you like, to the family std, these are all automatically available without having to put the std prefix on them. So earlier we saw, for example, that there was a vector type, which is std : vector. By writing this line here, I can just call it vector. I don't need to put the prefix std on the front. Here are a couple of, there's a short description, a long description. We put these in for our examples. If you make your own program, you don't really need these at all. You can get rid of that. Well, perhaps I should present this first, and then we can make a copy of xempty.c, and we can modify it to make our own program. So for the examples, they always contain a short description and a long description. They're supposed to summarize what the example is about. So this program itself does nothing whatsoever. That's actually slightly untrue. It initializes the CoCoA library ready for use, but then it does nothing after that. So really all it does is initializing the CoCoA library. This is an initial preamble. The code really starts around about here, where we do namespace CoCoA. And we've just seen namespace a bit earlier on. There was using namespace std. That's the one where all the functions and so on that belong to the standard template library are. All the CoCoA functions, we put in something called a namespace CoCoA. So namespace doesn't really do much other than attach a prefix to name. So a lot of functions in C++ actually have quite long names, perhaps a bit the same way that people often, if you take their full name, that's quite long. But mostly your friends you would just call by their first names or their given names. And that's what we do. So if we're inside the namespace CoCoA, then all functions that belong to the namespace CoCoA, to the family CoCoA, we can call by their first names. We don't need to put the prefix on. So let's move this up to the top of the screen. So this is the way I recommend that you write your programs. It works easiest here. So void, I think we've already seen that, means that this function returns no value. The function's name is program and it takes no arguments. The definition starts here and ends here, and this curly bracket here in fact corresponds to the end of the namespace CoCoA. I don't really want to go through what's happening below this line here. Main is actually the function that C++ requires that we define in a program. And then the rest of the stuff down here is an attempt to behave well if a CoCoA error occurs. So it prints out the error in a helpful, well, supposedly helpful way. So that's why later on you don't want to write all this. There are quite a few lines down here, and you might need to know a bit more C++ to understand what's going on. You don't need to understand this, just copy it. That's what we'll do for creating our own examples. Anyway, let's come back to program. This is where we're actually going to put code in. So we create something called a global manager. So we're inside namespace CoCoA. So strictly speaking, this is called CoCoA : global manager, but we're inside namespace CoCoA, so we can skip the prefix. I usually call it CoCoA foundations. It sets up the foundations for CoCoA. For example, it creates the ring of integers and the field of fractions, its fractions, that is the rational numbers. Signal watcher, you don't need to do this, so it's probably a good idea. If you want your program to be interruptible, so if it gets stuck in an infinite loop and you want to be able to know what's happening, then you can this watches out for sigint, that is if you type Control-C, Control-C. Anyway, that's a bit more advanced. You could skip this line if you want. Here, what happens on this line? So earlier on I'd already indicated that cout corresponds to a screen. So this line here is how we actually print something out in C++. This sort of double left arrow was chosen because it looks sort of mnemonic, so it has the idea of something sort of flowing towards cout. So if you think of cout as being the computer screen, then this takes short description. That's actually the string that we've seen just above, and it sends the short description to cout. And then we have another one here. If we want to print out several things, we don't separate them with commas, we separate them with this double left arrow. So endl, in this case, simply prints out a new line. So in C++, printing something out on cout never automatically prints a new line. CoCoA has that, it's the command print, but we normally use println because we want after printing, we want the computer to go to a new line. So it's normal in C++, you print out some things and then at the end you put endl. This line here actually tells the computer screen, if I print out a Boolean value on it, print it out using the strings true or false. Otherwise it uses the numbers 1 and 0, which are less easy to understand. So this is just for convenient reading. Again, if you want, you can comment this out. You can do some experiments, see what happens. And that's essentially all that the program does. This here, so we already know that the double slash at the beginning means a comment. Okay, actually, that was in CoCoA. It's also the same in C++. So a double slash is an end-of-line comment. So the double slash and everything else after it on that line are considered as comments in C++. So this yellow part here is just a big comment. The compiler will ignore it, and I've just put in a hint, put your code here. So if you want to do something, you will put your code here. So as far as C++ compiler is concerned, there's nothing here. It could just be empty space. So this is xempty. This is a lot of code that does essentially nothing. But it's handy to have all this extra baggage around. So C++ is very general, and we do need to set it up to say we want to set things up so that we can do calculations in CoCoALib or using CoCoALib, and that's what all this extra stuff is about. So let's actually do it. I'm going to make a copy somewhere else, so I'll tell it to save a copy, and I'll call it, let's say, demo.c. So we can now see at the bottom Emacs has changed its name. This is now associated. So this is a copy of what we had before, and we now want to put our code here. So we have, of course, we have to have an idea of what we're going to do in this code. So I'll try to do a quick one. Let's see. So if I remember correctly, I think factorial of 399 plus 1 is actually prime. So we could check that. Let's check that in CoCoALib, see how we might do it. So what we would do, okay, I'll put it in a comment. So this is in CoCoA 5, what we could do would be simply, actually we'd have to do is prob prime. Is prime won't like such a big value. Is probably prime, factorial of 399 plus 1. And with CoCoA 5, that would then print out true or false. So I'll do it this way in CoCoALib. So I'll just calculate the value. I'll call it big N. And that'll be 1 plus factorial of 399. Doesn't matter whether I add the 1 first, before, or afterwards. Write it the way that you think is most readable. So this would then calculate the value and put it into N. And now I want to see, well, if I just do is prob prime of N, well, we can try that. Let's see what happens. These comments, so I put my code here, so I'll just get rid of the comments. Doesn't really matter. So I have to save it. And now I have to, so in Emacs I can go into a shell, or you can open, yes, because I'm sharing only one window, I have to do this in Emacs. So I go to a shell, Oh, okay, I was doing some other things in the shell. Let's get rid of that junk there. Right. So I'm now in the shell. I'm in the correct directory. So we can just check if you want. There's, I think I used all uppercase, demo.c. So there's my file. And all I need to do to compile it is make demo. So hash here is a comment, and that's without the .c suffix. So it's the name but without the .c suffix. So this is what it actually does. So it says it's compiling demo, and the command it really runs is this great long command here, which is something you don't want to type in yourself. This is more complicated than what you'll see because I have quite a lot of external libraries included in my version. I try to test CoCoA with the most difficult setup, so I have lots of extra libraries here. Anyway, you don't need to understand that line. It's the correct line. It's compiled demo. Great. How do I... So compiler didn't give any errors. That's good. How do I actually run it? So in this case, so I'm in a Unix-like environment. I have to run it by doing /, the name of the program, demo, and without any suffix. So the .c suffix is the source code in C++. After compilation, it's put the results into a file with the same name but without the .c suffix. So on a Microsoft system, you probably have a .exe suffix on the end. We don't have that in a Linux or Unix world. We just get no suffix at all. So we can run it. This is a template program for template file for example programs. The program itself does nothing whatsoever. And is my number prime or not? It didn't tell me. What went wrong? So I'll flip back to my source code. This is demo.c. So okay, it printed out the short description. Okay, let's change the short description. Check whether factorial of 399 plus 1 is prime. In fact, of course, it'll be probably prime. So check that at the end of the string. So much like in CoCoA, we don't even need the long description. I'll get rid of that. Commands here have to end with a semicolon, but this is something you need to learn from a book about C++. You can guess quite a lot from these examples. So check whether that is prime. Great. So print out this. So we've calculated the big int n. We calculated is prob prime. But what happened to the answer? Well, in CoCoA 5, if we do nothing to an answer, it's automatically printed. In C++, if you do nothing to an answer, the compiler just throws it away. It calculates it, but then throws it away. So we actually have to tell it to print it out. So let's do that. And remember, we normally want to have an endl at the end as well. So we can do that. Now we save it again. And then we have to compile it again. So no point in running demo immediately because the file demo, if I run it again, that is what the compiler produced last time. So it'll be exactly the same. I have to compile it again with the make demo command, again without suffix. So that now creates a new compiled version, still called demo. To run it, I do /demo. We run it, and check whether that is prime. It prints out true. Okay, good. Maybe we should actually do something a little bit nicer here. We could print out a little message saying something like, is factorial of 399 plus 1 prime? Okay, so that now gives us a bit of a clue as to, so it gave a true or a false, but that's referring to what? We don't know, so let's try saving that. We have to recompile again, so every change you make you have to recompile. No, compiler is not happy, so what's it saying here? So it was compiling demo.c around about line 29, character 42 in the line, who cares about that, line 29. It expected a semicolon before isProb prime. It's printed out a line here. So it's expected, it's unhappy here where isProb prime came up. Let's go back. So that would actually be here. And the problem is, as I said, if we want to print out several things in one command, we have to separate them with these little less than operators. And I didn't put it in there. So I now put the less than operator. So the compiler detected that and tried to give a helpful error message. Now, of course, so compiler didn't succeed. So we have to try again. And with luck, it'll be happier this time. Oh, good. Now we can try running it again. Is factorial 399 plus 1 prime question mark true? Ooh, okay, that's a bit stuck together. So we probably want to put a couple of spaces here. So if we print out several things into cout, C++ puts nothing between. It doesn't put spaces, it doesn't put new lines, doesn't put commas, nothing. That's all our responsibility. Okay, here the program's working, we're just trying to make the output a bit nicer. In Emacs you can just recall an earlier command with a couple of key presses, instead of having to type it all in again. Okay, now this program's working quite a bit better. So we've actually got a first program working. And we didn't really need to know too much about compiling and so on. The only thing we really need to know is if we change the source code before we try running it again, we must compile. Because if we had an earlier version that compiled, then when we change the source code, it doesn't automatically delete the compiled version. So that will lie around, and so it could refer to some older version of the code. So there's a first program using CoCoALib. I'll try to add one more thing to this, and then we can take a break. So this is very easy, but Cocoa is mostly about using rings. I'll leave that there for the moment, and let's try to do something a bit more ambitious. So I want to choose a ring P for a polynomial ring. Now I'm not looking this up in the manual. You would have to look it up yourselves or look it up for an example. I'm going to call new polyring. Oh yes. Okay, this is a problem in my Emacs. I'll comment out these lines. Rather than delete them, I'll comment them out. Okay. For some reason, my Emacs does weird indentation like that. I don't know why. So I want a new polyring, but I have to say what the coefficients are and what the indeterminates are. And we have to use rather a different syntax. So I think I saw in one of the slides we can use the function symbols, and I'll just do it with just one indeterminate at the moment. So P here, I'll put a comment. I wouldn't normally do this, but this would correspond to P colon equals QQ of X in CoCoA 5. That's what we've done here. And we now want to create an element of that. I'll do this one. So we have to declare the types of every value. So I'm going to declare a polynomial G, ring LM G equals ring LM. I have to say what ring it's going to be in here. So there are several different ways of doing this. I'll do one here, and then I can put a string in. Let's see if I can remember it correctly. 2 times x to the power 4 plus 4 times x to the power 3 plus 5 times x squared plus 4 times x plus 2. There's a particular polynomial I happen to remember. Actually, I think I'll call it G1. And I'm going to create another one that's almost the same, so I'll just make a copy of that line. So I'll create another one here. I'm just going to alternate the signs here. So here I have 2 polynomials, G1 and G2. I can now do something like ring lm f equals g1 times g2. And then I'll print out the result. C out. So we've already learned it's a good idea when printing something out also to print out a little message saying what it is you're printing it out. So we have g1 times g2 is, and put a space or even two spaces at the end, and we print out the value f and endl at the end. Okay, let's see if that works. I've saved it, compile it again. We make demo. If I'm lucky I didn't make any syntax mistakes. Now we can run it again. Okay, I typed it in this time rather than recalling it. Okay, so we've just got CoCoALib to calculate the product of two polynomials. So this is actually an interesting example. Let's see. I can insert something here. Is G1 irreducible? No, can we factorize it or not? Is irrid G1? So why is my line got a funny color here? Anyone know? Just asked, had a quick look here, no one knew. I forgot to put a marker at the start of the string. No, it's okay. So Emacs was helping me there. It has this colored syntax, so I'd forgotten just to put a start at the string. Well, let's see what the... Supposing I hadn't noticed that and tried compiling it. The compiler is going to complain, that's for certain. Warning, missing terminating double quote character. Okay, so in fact we got quite a few mistakes, quite a few errors here. So warning, missing terminating that character, got it twice, I don't know why. And then compiler, despite this error, tries to go on and understand what's happening, and now it gets itself even more confused. Error, is was not declared in this scope, and then finally it gives up. So as we've seen before, it's best to try to concentrate on the first errors that we see, because afterwards the compiler might get confused. So the compiler did detect it and actually printed out something vaguely helpful, although as I've noticed before, as I showed in an example, the actual problem is right back here. I forgot the double quote character at the start of the string, not at the end of the string. So where the computer indicated as a problem is actually after where the real problem is. Let's put it in, we'll save it, and we try again. Don't worry about making the compiler do lots of work. It's designed to do lots of work. And we can run it. Is G1 irreducible? True. And we could then do the same thing with G2 if we want. Turns out, of course, they're both irreducible. And this was a counterexample to someone's conjecture. So I've just added that line there. Recompile. Run it again. Yes, they're both irreducible. So both of those polynomials had biggest coefficient 5, and yet when we multiply them together, the biggest coefficient we see here is 4. A couple of other things I could... Should I mention here? I'll mention it. So I've assigned the value to p is a variable here. Its value is a ring, but I've got no intention of changing the value of p. No intention at all. So I can actually put in const. That's telling the computer I'm initializing this variable to p, this variable p to this particular ring, and I do not plan to change it. By putting a const in there, if I do try to call some command which could or might change p, then the compiler will tell me, oh, wait, you shouldn't be doing this. You promised that you weren't going to change it. In fact, I can do the same for all of them if I want. if I'm certain I'm not going to change, say, G1 and G2, I can also declare those to be const. So these variables are now const. It's a property of the variable. So I cannot change, after this I can't change G1 and G2, but I could change F if I leave it like this. So I could also do, say, F gets, so what do you think happens if I do this? F gets, sorry, that's Emacs being annoying. F gets F squared, and we'll print that out. Yeah, great. So this would change, so, yes, assignment here is with an equals symbol. If we want to test equality, we have to do a double equals. That's a foible of C and C++. So let's do after squaring. Put this in. Yes. I'll get the indentation right. After squaring, recompile. It failed. Error, no match for operator hat. Operand types are ring element int. Good. We can't use hat for powers. We have to use the power function and put up with annoying auto indentation going on. Make demo. We can run it, and then after squaring we get some polynomial. That's one way of doing it. I'll show you one more quickly. We're running out of time here. It's almost lunchtime. So we have no use command in CoCoA 5. Can't do that. It's just not possible. But we can imitate it a little bit. So created this ring P. And so what I could do is I could do const ring lm x equals, so there are two options here. So one could be indet of P. So I want to have the first indeterminate of P. In fact, there's only one, but I need to choose it. Indexes start at 0. So that's one option. Or if you prefer, you can also use ring lm like we had before. I think that's probably actually more readable. Well, I'll leave it indet P0. So indexes start at 0. Now, so x is a variable that I declared const. So rather than using these strings, I could in principle type out the polynomial by itself. So I'll make a copy of this line, comment out one of them. Instead of using this ring lm here, I can actually type it in. Well, I can't use the hat thing. I'll copy the whole string. So I can't use hat for powers, which is actually very annoying. But it's we really can't do that. We have to use the power function. And then here, I think for better readability, we probably want to put in some extra spaces. So if you just want to do short ad hoc computations, I have to admit that CoCoALib is not terribly convenient. So if we were to write it out in full CoCoALib without using this string shortcut, we end up with a rather long and hard to read version like this. To be honest, the string version is much easier to read, but it's not very often that we actually want to have constant polynomials in our programs. Anyway, let's just check to make sure it works. Compile. Run. And we got exactly the same answer as before. So this is the way I recommend that you try to develop your own programs, at least to begin with, in CoCoALib. So I'm in the same directory where the examples are. I took a copy of xempty and then started adding my own code where where it said in the source to add my own code. We've got these double slashes that comment out a whole line. So I think it's also helpful to comment out lines like this, just in case later on you say, oops, what I had before actually worked better. I want to get it back. If it's just commented out, you can remove the comments. So I can do that. And now the program will do both. It'll check for, if I recompile it, it'll check to see whether that's prime, and then it'll calculate with the polynomials. And here it's then also useful that I've got these strings inside the printing, so I know what's happening here. So is factorial 399 plus 1 prime? True, yes. Is that irreducible? True, true, and so on. So I can see what I'm doing here. Okay, that was a crash course in writing your own code with CoCoALib. I think that's long enough. It's lunchtime here. I'll compress this and then upload it and send it. Hope that was helpful.